Welcome to the night sky and why ancient humans were obsessed with it. Hey guys, tonight we're diving into something a little different. Dim those lights, get comfortable, maybe grab a warm drink, and settle in. We're about to spend the next couple hours talking about ancient astronomers. And no, not the telescope-wielding, lab coat-wearing kind. I'm talking about people who looked up at the sky with nothing but their eyes, some sticks, maybe a rock or two, and somehow figured out when eclipses would happen. Wild, right? So here's the thing about ancient astronomy. It wasn't just nerds being nerdy, it was survival, it was religion, it was politics, it was everything. Because if you could predict when the seasons would change, when the floods would come, when to plant your crops, you were basically a wizard. And if you could predict an eclipse, forget it, you were a god. Tonight we're going to meander through the ancient world, from Mesopotamia to Mesoamerica, and meet some of the most patient, obsessive, mathematically gifted people who ever lived. People who spent their entire lives staring at dots in the sky and writing down when they moved. Sounds thrilling, I know, but stick with me, it gets weirdly interesting. Let's start with the big question. Why did ancient people care so much about the stars? Well, imagine you're living 5,000 years ago. No clocks, no calendars, no weather apps. You wake up when the sun rises, you go to bed when it sets, and in between, you're trying not to starve or get eaten by something. The sky is the only consistent thing in your life. The sun always rises in the east, the moon goes through its phases, the stars wheel overhead in the same patterns, night after night. And then you start noticing things, like, hey, when that really bright star appears just before dawn, the river floods a few weeks later. Or when the moon disappears completely, weird stuff happens. People get nervous, animals act strange. So you start paying attention, you start keeping track. This is how astronomy begins, not as science really, more like cosmic pattern recognition mixed with a healthy dose of superstition. The earliest astronomers weren't thinking about the universe in the way we do. They didn't know the Earth was a planet. They didn't know stars were distant suns. They thought the sky was a dome, maybe, or a ceiling, and the lights up there were gods, or spirits, or holes in the fabric of heaven. But they could still observe, they could still count, they could still predict. And that's what we're here to talk about. How they did it, the math, the patience, the obsessive record-keeping that went on for centuries. Because that's really what ancient astronomy was. It was people writing things down, generation after generation, until patterns emerged. Let's float over to ancient Mesopotamia, because that's where a lot of this started. Mesopotamia, clay tablets, and cosmic bureaucracy. Mesopotamia, the land between two rivers, modern-day Iraq. This is where civilization basically invented itself, and with civilization came the need to organize time. The Sumerians, Akkadians, Babylonians, Assyrians, they all contributed to what became the most sophisticated pre-telescopic astronomy in the world. The Mesopotamians were bureaucrats. They loved lists, they loved records, they wrote everything on clay tablets, and thank the gods they did, because we have thousands of these tablets, and they're filled with astronomical observations going back thousands of years. These people were obsessed with the sky, and I mean obsessed. They had professional astronomers, usually priests, whose entire job was to watch the heavens and write down what they saw. They'd sit on top of ziggurats, those big stepped pyramid things, and just stare. All night, every night, for years. And they wrote it all down. On the 15th day of the month, the moon was seen near the Pleiades. Venus appeared in the east before sunrise. Jupiter was stationary in the constellation of Cancer. Just pages and pages of the moon did this, Venus did that. Sounds boring as hell, right? But this is how they did it. This is how they figured out the patterns. Because here's the thing about celestial objects. They're predictable. The moon goes through the same cycle every 29.5 days. The planets wander around the zodiac in regular patterns. Once you've watched something for long enough, you can start to predict when it'll happen again. The Babylonians in particular got really good at this. By around 700 BCE, they had figured out something called the Saros cycle, which is an 18-year period after which eclipses repeat in almost the same pattern. This meant they could predict eclipses. Not perfectly, but pretty damn well, and that was huge. Imagine being a Babylonian king and your astronomer priest comes to you and says, "Your Majesty, on the 14th day of next month, the sun will go dark in the middle of the day." And then it happens. You're a genius. You're touched by the gods. You have power. Of course, if the astronomer got it wrong, he might lose his head, so there was some motivation to be accurate. The Babylonians also developed a sophisticated mathematical system for tracking the movements of the planets. They didn't understand why the planets moved the way they did. They didn't know about gravity or orbits, but they could describe how they moved with surprising precision. They broke the sky into 12 sections, which became the zodiac. They tracked the positions of the sun, moon, and planets against these background constellations. They developed tables and formulas for calculating where celestial objects would be at any given time. This was math-heavy stuff. The Babylonians used a base 60 number system, which is why we have 60 seconds in a minute and 60 minutes in an hour. They could do complex arithmetic, and they applied it to the heavens with an almost fanatical dedication. But let's be clear, this wasn't science in the modern sense. The Babylonians believed that the movements of the stars and planets were messages from the gods. They practiced astrology, not astronomy as we understand it. Every celestial event was an omen. A lunar eclipse might mean the king was in danger. A planetary conjunction could signal war or famine. So they watched the sky not just to understand it, but to read it, to divine the will of the gods and predict the future. Which, if you think about it, makes their achievements even more impressive. They were doing cutting-edge mathematics in service of what was essentially fortune-telling. But it worked. Their predictions were accurate enough to be useful, and their records were so detailed that later civilizations, including the Greeks, built on their work. Let's drift over to ancient Egypt now, because the Egyptians had their own relationship to the sky, and it was deeply tied to the most important thing in their world, the Nile. Egypt, the river, the dog star, and the calendar. Ancient Egypt, land of pyramids, pharaohs, and a river that determined whether you ate or starved. The Nile was everything. It flooded every year, depositing rich silt on the fields, making agriculture possible. But the flood had to come at the right time. Too early, too late, too much, too little, any of these could be a disaster. So the Egyptians needed to predict when the flood would come. And they figured out that they could do this by watching the stars. Specifically, they watched a star called Sirius. The Greeks called it the dog star because it's the brightest star in the constellation Canis Major. The Egyptians called it Sopdet, and they loved it. Every year, after being invisible for about 70 days, Sirius would reappear in the eastern sky just before dawn. This is called the heliacal rising, and the Egyptians noticed that Sirius reappeared right around the time the Nile started to flood. So they used Sirius as a celestial alarm clock. When Sopdet came back, it was time to get ready for the flood. This was so important to them that they based their calendar on it. The Egyptian civil calendar had 365 days, divided into 12 months of 30 days each, plus 5 extra days at the end. It wasn't perfect. The actual solar year is about 365.25 days, but it was close enough for government work. And it was one of the first solar calendars in history. The Egyptians were less into math than the Babylonians. They didn't develop the same kind of predictive astronomy, but they were incredible observers. They paid attention to the sky, they tracked the movements of the stars, and they used that knowledge in practical ways. They also built some of the most astronomically aligned structures in the ancient world. The pyramids of Giza, for example, are aligned with incredible precision to the cardinal directions. The Great Pyramid is aligned to true north with an error of less than 1/15 of a degree. How did they do that without compasses? They used the stars. One theory is that they used a pair of stars in the northern sky and observed their positions relative to a vertical plumb line. When the two stars were level with each other, the vertical line pointed true north. It's simple, elegant, and it worked. The Egyptians also had a pretty good understanding of the night sky. They divided it into 36 sections called decans, each associated with a group of stars. As the Earth rotates, different decans rise above the horizon at different times of the night. By watching which decan was rising, you could tell what time it was. Basically, the stars were a clock. They painted these decans on the ceilings of tombs and temples. If you ever get a chance to look at the astronomical ceiling in the tomb of Senenmut, do it. It's gorgeous and weird and full of stars and constellations that we still can't fully identify. But here's the thing about Egyptian astronomy. It was deeply religious. The sky wasn't just useful for telling time or predicting floods. They were gods. The sky was the body of the goddess Nut, arching over the earth. The sun was the god Ra, traveling across her body in a boat during the day, then journeying through the underworld at night. When the pharaoh died, his soul was supposed to ascend to the sky and become a star. The pyramids, with their shafts pointing towards certain stars, may have been designed to help the pharaoh's soul make that journey. So, Egyptian astronomy was a mix of practical observation and profound religious belief. The sky was both a tool and a secret mystery. Now let's hop over to ancient China, where astronomy was a matter of imperial importance, and getting it wrong could cost you your job or your head. China, celestial bureaucrats and the mandate of heaven. Ancient China had a unique relationship with astronomy because the emperor's authority depended on it. The emperor was the son of heaven, and his right to rule came from the mandate of heaven. If the heavens were happy, things went well. If the heavens were upset, disasters happened. And how did you know if the heavens were happy or upset? You watched the sky. Unusual celestial events, comets, eclipses, supernovae, were seen as omens. A comet could mean the emperor was losing the mandate of heaven. An eclipse could signal political upheaval. So it was really important to predict these things in advance. If the astronomers could say, hey, there's going to be an eclipse next month, but it's fine, we knew it was coming, then it wasn't an omen, it was just astronomy. But if an eclipse happened without warning, that was bad. That meant the heavens were sending a message, and the message was probably, your emperor sucks. So Chinese emperors employed official astronomers. These were government positions, part of the imperial bureaucracy, and these astronomers kept meticulous records. I mean, we're talking thousands of years of continuous observation. The Chinese were probably the best record keepers in the ancient world. They documented eclipses, comets, planetary positions, sunspots, supernovae, everything. And because they did this for so long, their records are incredibly valuable to modern astronomers. We can use Chinese astronomical records to study historical events like the supernova of 1054, which created the Crab Nebula. The Chinese also developed their own calendar, which was a luno-solar calendar. This means it was based on the moon's phases and the sun's position. Months began with the new moon, and the year was adjusted periodically to keep it in sync with the seasons. It was complicated, and calculating it correctly required serious astronomical knowledge. They divided the sky into 28 lunar mansions called shu, which were basically segments of the moon's path through the sky. These were used for timekeeping and astrology. And yes, Chinese astronomy was deeply tied to astrology. Every celestial event had meaning. The position of the planets, the appearance of comets, the occurrence of eclipses, all of these were analyzed for their political and social implications. Chinese astronomers also made some impressive technological achievements. They built armillary spheres, which are mechanical models of the celestial sphere. These devices could be used to measure the positions of stars and planets with remarkable accuracy. By the time of the Han Dynasty, around 100 BC, Chinese astronomers had cataloged over 1,400 stars. They had identified the 5 visible planets and tracked their movements. They had figured out the length of the solar year to within a few minutes. But they were also constrained by their role as imperial servants. Astronomy was knowledge that was closely guarded. It was a state secret. Only the emperor and his official astronomers were supposed to have access to it. Anyone else practicing astronomy could be accused of sedition, because unauthorized astronomy could be used to challenge the emperor's legitimacy. So, Chinese astronomy was sophisticated, highly organized, and deeply political. The astronomers were good at what they did, but they were also acutely aware that their careers, and possibly their lives, depended on getting it right. Now let's hop westward now to ancient India, where astronomers were doing some truly impressive mathematical work.
India, trigonometry, planetary periods, and the cosmic cycles. Ancient Indian astronomy is wild because it combined incredibly sophisticated mathematics with cosmological ideas that were, let's say, creative. The Indians had a different worldview than the Babylonians or Greeks. Time in Indian cosmology operated on absolutely vast scales. We're talking billions of years. The universe went through endless cycles of creation and destruction, and human history was just a tiny blip in this cosmic drama. But within that framework, Indian astronomers did some really impressive work. They developed trigonometry. They calculated the lengths of planetary orbits, they estimated the size of the Earth, and they did all of this more than 1,000 years before Europe caught up. One of the earliest Indian astronomical texts is the Vedanga Jyotisha, which dates back to around 1400 BCE. It's a manual for calculating the positions of the sun and moon, mostly for the purpose of scheduling religious rituals, because in ancient India, like everywhere else, astronomy was tied to religion. But the real golden age of Indian astronomy came later, during the Gupta period, around the 5th and 6th centuries CE. This is when astronomers like Aryabhata and Varahamihra were working. Aryabhata was a genius. In 499 CE, when he was 23 years old, he wrote a book called the Aryabhatya. It's only 118 verses long, but it's packed with information. In it, Aryabhata presents methods for calculating the positions of the planets, the times of eclipses, and the length of the solar year. He also proposes that the Earth rotates on its axis, which was a radical idea at the time. Most people in the ancient world thought the Earth was stationary and the sky rotated around it. But Aryabhata said no, the Earth spins, and that's why the stars appear to move. He was right, of course, though it would be 1,000 years before this idea gained widespread acceptance. Aryabhata also calculated the value of pi to 4 decimal places, and he developed an early form of trigonometry using sine functions. This was cutting-edge mathematics, and it was essential for his astronomical calculations. Indian astronomers were particularly good at calculating planetary periods. They figured out how long it took each planet to complete its orbit with impressive accuracy. They also developed tables for predicting planetary positions, which were more accurate than anything available in Europe at the time. Varahamihra, a contemporary of Aryabhata, wrote an encyclopedic work called the Pancha Siddhantika, which summarized 5 different astronomical systems. He was trying to synthesize knowledge from Greek, Babylonian, and Indian sources. Indian astronomy didn't develop in isolation, it was part of a broader network of knowledge that stretched across Asia. Indian astronomers also built observatories and astronomical instruments. The most famous is probably Jantar Mantar in Jaipur, built in the 18th century, but there were earlier structures as well. They used gnomons, sundials, and water clocks to measure time and the positions of celestial objects. But here's where Indian astronomy gets a bit weird, at least from a modern perspective. Indian cosmology was fantastically elaborate. The Earth was flat, or sometimes round, and it sat on the back of elephants, which stood on a giant turtle, which floated in a cosmic ocean. The sun and moon were carried across the sky in chariots pulled by divine beings. And yet, within this mythological framework, Indian astronomers were doing serious, accurate mathematical work. They could predict eclipses. They could calculate planetary positions. They understood that celestial motions followed regular, predictable patterns. So, Indian astronomy was this fascinating mix of empirical observation, advanced mathematics, and elaborate mythology. It didn't fit neatly into the Greek model of rational geometric astronomy, but it was no less sophisticated.
All right, let's head to the Americas now, because the Maya had their own astronomical tradition, and it was absolutely remarkable. The Maya, Venus, the calendar, and the end of the world, sort of. The Maya civilization flourished in Mesoamerica, modern-day Mexico, Guatemala, Belize, and Honduras, from around 2000 BCE until the Spanish conquest in the 16th century, and they were absolutely obsessed with time. The Maya didn't have telescopes, they didn't have metal tools, they didn't have the wheel, at least not in any practical sense, but they had incredible astronomical knowledge, and they encoded it in their architecture, their calendar systems, and their codices. The Maya believed that time was cyclical. History repeated itself in predictable patterns. If you could understand these cycles, you could predict the future. So they watched the sky, they tracked the movements of the sun, moon, and planets, and they developed one of the most complex calendar systems in history. Actually, they had multiple calendars. The Tzolk'in was a 260-day ritual calendar. The Hab was a 365-day solar calendar. These two calendars meshed together like gears, creating a longer cycle called the calendar round, which repeated every 52 years. And then there was the long count, which tracked days from a mythological starting point in 3114 BCE. You know how everyone freaked out in 2012 because the Maya calendar was supposedly ending and the world was going to end? Yeah, that was based on a misunderstanding of the long count. The Maya calendar wasn't ending, it was just completing a cycle and starting over. It's like saying the world ends every December 31st because the calendar runs out of days. Anyway, the Maya used these calendars to schedule agricultural activities, religious ceremonies, and political events, and they aligned them with astronomical observations. The Maya were particularly interested in Venus. They tracked its movements with obsessive precision. Venus is visible as the morning star for about 263 days, then it disappears for about 50 days, then it reappears as the evening star for another 263 days, then disappears again for about 8 days. The whole cycle takes about 584 days. The Maya figured this out, and they incorporated it into their calendar system. They had tables for predicting when Venus would appear and disappear. They believed that Venus was associated with war and sacrifice, so its movements were seen as omens. Battles were timed to coincide with specific phases of Venus. The Maya also tracked eclipses. The Dresden Codex, one of the few surviving Maya books, contains detailed eclipse tables. These tables show that the Maya understood the Saros cycle, the same 18-year eclipse cycle that the Babylonians had figured out. Whether they discovered this independently or learned it through cultural contact is still debated, but either way, it's impressive. The Maya built their cities with astronomical alignments. At Chichen Itza, there's a famous pyramid called El Castillo. During the spring and autumn equinoxes, the setting sun creates a shadow pattern on the pyramid that looks like a serpent descending the staircase. This wasn't an accident. The Maya designed it that way. At Uxmal, there's a building called the Governor's Palace, which is aligned with the southmost rising point of Venus. At Karakol, there's a circular observatory with windows that align with specific celestial events. The Maya didn't write about astronomy the way the Greeks did. They didn't have theories about the structure of the cosmos, but they were master observers and record keepers. They watched the sky, they tracked the patterns, and they used that knowledge to organize their world. Greece, geometry, and the birth of theoretical astronomy. All right, let's drift over to ancient Greece, where astronomy took a philosophical turn. The Greeks were different from everyone we've talked about so far because they weren't just content to observe and predict. They wanted to understand. They wanted to know why the heavens moved the way they did. They wanted a theory. This is where astronomy starts to look more like what we'd recognize as science. Less, the gods are doing stuff, and more, there must be underlying principles we can figure out. The early Greek philosophers started asking questions that seem obvious now, but were revolutionary at the time. Is the Earth flat or round? Does it move or is it stationary? What are the stars made of? How far away are they? Thales of Miletus, who lived around 600 BCE, was one of the first. He's supposed to have predicted a solar eclipse in 585 BCE, though how he did it is unclear. He probably used Babylonian tables, because the Greeks were definitely in contact with Mesopotamian astronomy by this point. But the fact that a Greek philosopher was even trying to predict eclipses shows a new way of thinking. Pythagoras, the triangle guy, came along around 570 BCE. He and his followers believed that the universe was fundamentally mathematical. Everything could be understood through numbers and geometry. This was a huge idea. It meant the cosmos wasn't just the whim of the gods, it was orderly, rational, predictable. The Pythagoreans also figured out that the Earth was round, not flat, spherical. They observed that during a lunar eclipse, the Earth's shadow on the moon was curved. Only a sphere casts a round shadow from every angle. Boom, round Earth. Aristotle, around 350 BCE, expanded on this. He gave multiple arguments for a spherical Earth. The North Star appears at different heights in the sky as you travel north or south. Ships disappear hull first over the horizon. The Earth's shadow during lunar eclipses is always circular. These were solid observational arguments, and they convinced most educated Greeks that the Earth was a sphere. But here's where things get interesting. The Greeks developed two competing models of the cosmos, and both were wrong, but in different ways. The first was the geocentric model, with the Earth at the center. This made intuitive sense. The Earth feels stationary. The sun, moon, stars, and planets all appear to revolve around us. So the early Greek astronomers, including Aristotle, developed elaborate geometric models with the Earth in the middle and everything else moving around it in perfect circles. Because the Greeks were obsessed with circles. Circles were perfect. The heavens were perfect. Therefore, celestial motion had to be circular. This was more philosophy than observation, but it stuck. The problem was the planets didn't move in simple circles. They wandered. They sped up and slowed down. Sometimes they even moved backward, retrograde motion. This was a nightmare for the geocentric model. So astronomers started adding complications. Epicycles. Imagine a planet moving in a circle, but that circle itself moves along another circle around the Earth. This is an epicycle, and if you add enough of them, you can make the model match observations pretty well. It's clunky, but it works. Ptolemy, working in Alexandria around 150 CE, perfected this system. His book, The Alchemist, was the definitive astronomical text for over 1,000 years. It contained detailed tables for predicting planetary positions, and it was pretty accurate. But it required dozens of epicycles and other geometric tricks. Now, while most Greeks were working on geocentric models, a few weirdos had a different idea. What if the Earth wasn't at the center? What if it moved? Aristarchus of Samos, around 270 BCE, proposed a heliocentric model. The Sun at the center, the Earth and other planets orbiting around it. This would explain retrograde motion much simpler. When we pass Mars in our orbit, it appears to move backward against the stars. Easy. But Aristarchus's idea didn't catch on. Why? Because it contradicted common sense. The Earth doesn't feel like it's moving. And if the Earth is moving around the Sun, then the stars should shift their positions as we orbit. Parallax. But the Greeks couldn't see any parallax. Of course, this is because the stars are incredibly far away, but they didn't know that, so most astronomers rejected heliocentrism. Still, the Greeks made incredible calculations. Eratosthenes, around 240 BCE, measured the circumference of the Earth. He noticed that at noon on the summer solstice in Cyrene, the sun was directly overhead. But in Alexandria, 800 kilometers north, it wasn't. It was about 7 degrees off vertical. Using geometry, he calculated that if 7 degrees equals 800 kilometers, then 360 degrees, a full circle around the Earth, equals about 40,000 kilometers, which is remarkably close to the actual value of 40,075 kilometers. Not bad for ancient math. Hipparchus, around 150 BCE, did something equally impressive. He compiled the first comprehensive star catalog,
listing the positions of over 850 stars, and by comparing his observations with older records, he discovered precession. Precession is the slow wobble of the Earth's axis. It's like a spinning top that wobbles as it spins. This wobble takes about 26,000 years to complete a full cycle, and it means that the position of the North Star slowly changes over thousands of years. Hipparchus figured this out just by comparing star positions across a couple hundred years. Meticulous observation for the win. Greek astronomy was a mix of brilliant observation, clever mathematics, and philosophical assumptions that sometimes led them astray. They were so committed to perfect circular motion that they couldn't accept a simpler heliocentric model. But they laid the groundwork for everything that came after. Let's move forward in time now to the Islamic Golden Age, where Greek astronomy was preserved, expanded, and perfected.
The Islamic Golden Age, saving and improving Greek astronomy. So here's the thing. After the fall of the Roman Empire, Europe kind of forgot about a lot of classical knowledge. Libraries burned, manuscripts were lost, and for a few centuries, European astronomy went backward. But in the Islamic world, it was a different story. Starting around the 8th century CE, scholars in the Middle East, North Africa, and Spain were translating Greek, Persian, and Indian astronomical texts into Arabic. They preserved this knowledge, studied it, and improved on it. The Islamic Golden Age produced some of the greatest astronomers in history, and they made contributions that were essential to the later scientific revolution in Europe. Let's start with al-Khwarizmi, who worked in Baghdad around 820 CE. He wrote astronomical tables based on Indian and Greek sources, but he refined them and made them more accurate. He also wrote a book on algebra. The word algebra comes from the Arabic al-Jabr, which became essential for astronomical calculations. Then there's al-Battani, working around 900 CE in Syria. He observed the sky for decades and produced incredibly accurate measurements of the length of the solar year, the precession of the equinoxes, and the obliquity of the ecliptic, the tilt of the Earth's axis. His measurements were more accurate than Ptolemy's, and they remained the best available for centuries. Al-Battani also improved the theory of planetary motion. He realized that the distance between the Earth and the Sun varies throughout the year, which means the Earth's orbit isn't a perfect circle. This was a key observation, though he still worked within a geocentric framework. In the 10th century, astronomers in Persia built huge observatories equipped with sophisticated instruments. These weren't just buildings, they were research institutions. Astronomers worked there for years, making systematic observations and refining their calculations. One of the most important was the Marageh Observatory in Iran, founded around 1259 CE by Nasir al-Din al-Tusi. Al-Tusi was trying to fix problems with Ptolemy's model. Ptolemy's epicycles worked, but they violated the principle of uniform circular motion. Al-Tusi developed a clever geometric device called the Tusi couple, which could produce straight-line motion from circular motion. This was mathematically sophisticated stuff. Later, at the Samarkand Observatory in Uzbekistan, Ulugh Beg and his team compiled the Zij-e-Sultani, one of the most accurate star catalogs ever produced in the pre-telescopic era. They measured the positions of over 1,000 stars to within a fraction of a degree. Islamic astronomers also made significant contributions to observational instruments. They improved the astrolabe, a handheld device for measuring the positions of stars and planets. They built huge mural quadrants for measuring angles in the sky. They developed better methods for calculating time and direction, which was important for determining the times of Islamic prayers and the direction of Mecca. And here's something interesting. Islamic astronomers were more willing than the Greeks to question Ptolemy. They respected his work, but they weren't afraid to point out his flaws. They developed alternative models, refined his calculations, and pushed the boundaries of geocentric astronomy as far as it could go. But they never made the leap to heliocentrism, not publicly anyway. There's some evidence that a few Islamic astronomers toyed with the idea, but it never became mainstream. The geocentric model, with all its complications, remained dominant. Still, when European astronomers in the Renaissance started rediscovering classical astronomy, they weren't reading Ptolemy and Greek. They were reading Latin translations of Arabic translations and commentaries. Islamic astronomers had kept the flame alive and made it brighter. Now let's shift gears and head out into the Pacific Ocean, where Polynesian navigators were using the stars in a completely different way. Polynesian wayfinding, navigating by stars, waves, and birds. The Polynesians didn't have written records. They didn't build observatories. They didn't do math on clay tablets, but they had one of the most impressive bodies of astronomical knowledge in the ancient world, and they used it to navigate across thousands of miles of open ocean. Think about that for a second. The Pacific Ocean is enormous. Island chains are tiny specks separated by vast stretches of water. There are no landmarks, no roads, no GPS, and yet, starting around 3,000 years ago, Polynesians were sailing from island to island, settling places as far apart as Hawaii, Easter Island, and New Zealand. How did they do it? Stars and waves and birds, and an incredible amount of accumulated knowledge passed down through generations. Polynesian navigation, or wayfinding, is a holistic system. It's not just about astronomy, but astronomy is a huge part of it. Navigators memorized the positions of hundreds of stars. They knew which stars rose and set at specific points on the horizon, and they used these as directional markers. If you're trying to sail from Tahiti to Hawaii, you aim for the star that rises in that direction and follow it.
But stars move. They rise and set throughout the night, so navigators had to know the entire path of each star. They memorized sequences of stars, star paths, that they could follow across the sky. The Southern Cross, for example, was a key constellation. It's visible in the southern hemisphere and rotates around the south celestial pole. By observing its orientation, navigators could determine direction. Polynesian navigators also used zenith stars, stars that pass directly overhead at specific latitudes. If you know that a particular star passes directly overhead at your destination, you can sail until that star is at its zenith and you know you're at the right latitude. Then you just sail east or west until you find the island. But navigation wasn't just about stars. Polynesians also read the ocean. They understood wave patterns, currents, and swells. Waves reflect off islands, creating interference patterns that an experienced navigator can detect from miles away. It's like reading invisible signposts in the water. They also watched for birds. Certain seabirds fly out from land in the morning and return at night. If you see these birds in the evening, flying in a particular direction, you know there's land that way. Follow the birds. And then there's dead reckoning, keeping track of your speed and direction to estimate your position. Polynesians did this mentally, constantly updating their mental map of where they were relative to islands, currents, and stars. This knowledge wasn't written down. It was taught orally, from master navigators to apprentices. It took years to learn. You had to memorize star paths, wave patterns, bird behavior, and more. You had to develop an intuitive sense of the ocean and the sky. And it worked. Polynesians settled virtually every habitable island in the Pacific. They made voyages of thousands of miles, often intentionally, sometimes returning to the same island years later. This wasn't accidental drifting. This was deliberate, skilled navigation. When Europeans first encountered Polynesian navigators, they were skeptical. How could these people with no instruments navigate better than European sailors with compasses and sextants? But they did. And in recent decades, there's been a revival of traditional wayfinding. People like Mao Pi Lug and Nainoa Thompson have shown that these techniques still work. So Polynesian astronomy wasn't about predicting eclipses or building cosmological models. It was practical. It was about survival and exploration. And it was just as sophisticated in its own way as anything the Greeks or Babylonians did.
Let's float back to dry land and talk about Stonehenge and other megalithic structures, because people love to speculate about ancient stone circles and astronomy. Stonehenge and megaliths, ancient observatories, or just really big calendars. Stonehenge. It's mysterious, it's iconic, and people have been arguing about what it was for since basically forever. Was it a temple? A burial site? An astronomical observatory? A place for healing? A giant calendar? Yes, all of the above? Probably some combination, honestly. Stonehenge is located in Wiltshire, England, and it was built in stages over about 1,500 years, starting around 3000 BCE. The big stones, the sarsens and bluestones, were erected around 2500 BCE, which makes them older than the pyramids of Giza. And they're arranged with some pretty clear astronomical alignments. The most famous alignment is with the summer solstice. On the longest day of the year, the sun rises directly over a stone called the heel stone and shines into the center of the monument. Thousands of people gather at Stonehenge every year to watch this. It's quite the party, apparently. There's also a winter solstice alignment. The sun sets along the main axis of Stonehenge on the shortest day of the year. Some archaeologists think this might have been even more important to the builders than the summer solstice. So, yeah, Stonehenge was definitely designed with the sun's movements in mind. But was it an observatory? That's harder to say. An observatory implies systematic observation and record keeping. We don't have evidence of that. What we have is a monument aligned with celestial events. It could have been a temple where solstice celebrations happened. It could have been a calendar marking important times of the year. It could have been both. Some researchers have proposed that Stonehenge was also used to predict eclipses. There's a ring of holes called the Aubrey holes that might have been used for counting lunar cycles. If you move markers around these holes, you can track the 18.6-year cycle of lunar eclipses. It's a neat theory, but it's hard to prove. What we do know is that Stonehenge was important. People dragged stones weighing up to 25 tons from quarries 25 kilometers away. The blue stones came from Wales, over 200 kilometers away. This was a massive effort, requiring thousands of workers over many years. You don't do that for trivial. And Stonehenge isn't unique. There are megalithic structures all over Europe with astronomical alignments. Newgrange in Ireland, built around 3200 BCE, has a passage that's illuminated by the rising sun on the winter solstice. Callanish in Scotland, Carnac in France, Menandra in Malta, all of these have solar or lunar alignments. These structures show that Neolithic people in Europe were paying attention to the sky. They were tracking the movements of the sun and moon. They were marking important dates in the calendar. But we have to be careful not to overinterpret. Just because something is aligned with the sun doesn't make it an observatory. Medieval churches are aligned east-west, but that doesn't make them astronomical instruments. It's symbolic. Still, there's something haunting about standing at Stonehenge on the summer solstice and watching the sun rise over the heel stone, and knowing that people 4,500 years ago stood in the same spot and watched the same thing. They didn't understand astronomy the way we do. They didn't know about orbits or axial tilt, but they understood the rhythm of the sky, and they built something that would last for millennia to mark it. Let's float back to dry land and talk about the ancestral Puebloans of the American Southwest.
The ancestral Puebloans, sometimes called the Anasazi, lived in what's now the southwestern United States, Arizona, New Mexico, Colorado, and Utah, from about 100 CE to 1300 CE. They're famous for their cliff dwellings, like the ones at Mesa Verde, but they also had a sophisticated understanding of astronomy. And we know this because they left clues carved into the rock. At a place called Chaco Canyon in New Mexico, there's a site called Fajada Butte. Near the top of this butte, there are 3 large stone slabs leaning against a cliff face. Behind them, carved into the cliff, are 2 spiral petroglyphs. Here's the cool part. As the sun moves across the sky throughout the year, it casts shadows and creates patterns of light that interact with these spirals. At the summer solstice, a dagger of light pierces through the center of the larger spiral. At the winter solstice, 2 daggers of light frame the edges of the spiral. At the equinoxes, a smaller dagger bisects the smaller spiral. This is called the sun dagger, and it's either an incredibly sophisticated astronomical marker or the luckiest accident in history. Most archaeologists lean toward intentional design because the ancestral Puebloans built a lot of structures with solar alignments. At Chaco Canyon, many of the great houses, large multi-story buildings, are aligned with solar or lunar events. Windows, doors, and walls are positioned to catch specific angles of sunlight at specific times of the year. Why did they care? Probably for the same reasons everyone else did: agriculture. The ancestral Puebloans were farmers, growing corn, beans, and squash in a harsh, arid environment. Knowing when to plant and when to harvest was crucial. The solstices and equinoxes marked important transitions in the agricultural calendar. But it was also probably religious. The sun was sacred to many Native American cultures. Marking its movements might have been a way of honoring it, connecting with it, ensuring that it would continue its journey across the sky. The ancestral Puebloans didn't leave written records, so were mostly interpreting their astronomy from the physical evidence they left behind. But that evidence suggests they were careful observers of the sky, and they incorporated that knowledge into their architecture and their rituals. Now let's jump forward a bit in time and talk about something really specific: how ancient people dealt with the problem of leap years. The leap year problem, or why calendars are harder than you think. Okay, so here's a problem that seems simple but drove ancient astronomers absolutely crazy: making a calendar that doesn't drift. The Earth takes about 365.25 days to orbit the Sun. Not 365, not 366, about 365.25. That extra quarter day is a nightmare if you're trying to make a calendar that stays in sync with the seasons. If you just make a 365-day calendar and ignore the extra quarter day, your calendar drifts. After 4 years, you're a full day behind. After 40 years, you're 10 days behind. After 400 years, you're over 3 months off. Suddenly, you're celebrating the summer solstice in the fall. Your agricultural calendar is useless. Everyone is confused and probably angry. So ancient civilizations had to figure out how to deal with this, and different cultures came up with different solutions. The Egyptians, as we mentioned earlier, used a 365-day calendar and just accepted the drift. Their civil calendars slowly got out of sync with the seasons, completing a full cycle every 1460 years. This was fine for administrative purposes, but they also kept track of the heliacal rising of Sirius, which didn't drift, so they had a backup. The Babylonians used a lunisolar calendar, based on the phases of the moon. A lunar month is about 29.5 days, so 12 lunar months add up to about 354 days. This is 11 days short of a solar year. So every few years, they'd add an extra month to keep things in sync. It was a bit ad hoc. Sometimes the king would just decree an extra month if it seemed like things were getting out of whack, but it worked well enough. The Chinese used a similar system, adding leap months as needed to keep their lunisolar calendar aligned with the seasons. By the time of the Han Dynasty, they had developed complex mathematical rules for when to insert these leap months. But the real breakthrough came from the Romans, or more specifically, from Julius Caesar. The Roman calendar before Caesar was a mess. It had 355 days, and they added an extra month every couple of years to keep it aligned. But the system was so politicized that officials would add or skip leap months to extend their terms or mess with their rivals. By 46 BCE, the calendar was 3 months out of sync with the seasons. Caesar, being Caesar, decided to fix this. He consulted with an astronomer named Sosigenes of Alexandria, who proposed a solar calendar with 365 days and an extra day every 4 years. This is the Julian calendar, and it was implemented in 45 BCE. To get everything back on track, Caesar decreed that the year 46 BCE would have 445 days. That's right, 445 days. It was called the Year of Confusion, which seems appropriate. But after that, the calendar worked beautifully. Well, mostly. The Julian calendar has an average year length of 365.25 days, which is very close to the actual solar year, but it's not exact. The real solar year is about 365.2422 days. That means the Julian calendar gains about 11 minutes per year, or 1 day every 128 years. This doesn't sound like much, but over centuries it adds up. By 1582 CE, the calendar was 10 days off. The spring equinox, which was supposed to fall around March 21st, was happening on March 11th. This was a problem for the Catholic Church because it threw off the calculation of Easter. So, Pope Gregory XIII introduced a new calendar, the Gregorian calendar, which is the one we use today. The rule is, leap years happen every 4 years, except for years divisible by 100, which are not leap years, unless they're also divisible by 400, in which case they are leap years. Got that? So 2000 was a leap year because it's divisible by 400, but 1900 was not a leap year because it's divisible by 100, but not by 400. This rule makes the average year length 365.2425 days, which is very, very close to the actual solar year. But we're getting ahead of ourselves. The point is, ancient astronomers struggled with this problem for thousands of years. They knew the year wasn't a neat 365 days. They could observe that. But finding a calendar system that was both accurate and practical took centuries of trial and error. And here's a fun fact. Some cultures said screw it and didn't even try to align their calendar with the solar year. The Islamic calendar, for example, is purely lunar. 12 lunar months, no leap months, no attempt to sync with the seasons. This means Islamic months drift through the solar year, completing a full cycle every 33 years or so. Ramadan, for instance, happens at different times of the year depending on where you are in the cycle. This works fine if your calendar is primarily for religious purposes, which is the Islamic calendar is, but it would be a disaster for agriculture, which is why most ancient civilizations that depended on farming used some form of lunisolar or solar calendar. Calendars are weirdly complicated. They're this intersection of astronomy, mathematics, religion, politics, and practicality. And ancient astronomers had to figure all of this out through observation and calculation without computers or precise clocks. Let's move on and talk about timekeeping in general, because telling time was another huge challenge for ancient people. Telling time without clocks, sundials, water clocks, and celestial timekeeping. Okay, so you're living in ancient times. You don't have a watch, you don't have a clock. How do you know what time it is? Well, during the day, you can look at the sun. The sun rises in the east, climbs to its highest point at noon, and sets in the west. Its position tells you roughly what time it is, but roughly isn't always good enough. So ancient people invented sundials. A sundial is just a stick or a wedge that casts a shadow. As the sun moves across the sky, the shadow moves, and you can mark the hours on a surface. The Egyptians were using sundials by at least 1500 BCE. They had different types, simple shadow clocks, more complex obelisks that cast shadows, and portable sundials that you could carry with you. Because, of course, you need a portable sundial. The Greeks and Romans refined sundials, making them more accurate and decorative. They understood that the angle of the sundial had to be adjusted based on your latitude. A sundial designed for Athens wouldn't work properly in Rome because the sun's path across the sky is different at different latitudes.
But sundials have a problem. They only work when the sun is shining. At night or on cloudy days, you're out of luck. For nighttime timekeeping, ancient astronomers used the stars. As we mentioned earlier, the Egyptians divided the night sky into decans. By watching which stars were rising, you could estimate the time. This worked, but it required you to know the stars really well, and it wasn't super precise. The Greeks and Romans also used star clocks. They'd observe the position of specific stars or constellations and use that to estimate the time. But again, this was more of a rough estimate than an exact measurement. For more precise timekeeping, ancient people used water clocks or clepsydras. The basic idea is simple. Water drips from one container into another at a steady rate, and you measure the time by how much water has moved. The Egyptians were using water clocks by around 1600 BCE.
The Greeks and Romans improved on them, creating elaborate devices with multiple chambers, gears, and floats to regulate the flow of water and indicate the hours. Water clocks had advantages over sundials. They worked day or night, rain or shine, and they could be made quite accurate as long as the water flow was steady. The Chinese also developed sophisticated water clocks. By the Song dynasty, around 1000 CE, they were building enormous clockwork mechanisms powered by water. These weren't just clocks, they were astronomical instruments that could track the positions of the sun, moon, and planets. But here's the thing, all of these timekeeping methods were relative. They divided daylight into 12 hours and nighttime into 12 hours, but the length of an hour changed throughout the year. In summer, when days are long, a daytime hour was longer than a nighttime hour. In winter, it was the opposite. This system, called temporal hours or seasonal hours, was used throughout the ancient and medieval world. It seems weird to us, but it made sense in a world where most activities were tied to daylight. The idea of hours of equal length, equinoctial hours, existed, but it was mostly used by astronomers and wasn't widely adopted for everyday life until mechanical clocks became common in the late Middle Ages. So, ancient timekeeping was a mix of practical observation, clever engineering, and a willingness to accept that time was a bit flexible depending on the season. Now let's talk about something that ancient astronomers didn't fully understand, but definitely noticed: comets and meteors. Comets, meteors, and other scary things in the sky. Comets terrified ancient people, and honestly, you can't blame them. Imagine you're living a few thousand years ago. The sky is predictable. The sun rises and sets, the moon goes through its phases, the stars stay in their constellations, the planets wander, but they wander in predictable ways. And then one night, there's a new light in the sky. It's bright. It has a tail, it's moving, and it stays there for weeks or months, getting brighter or fainter, moving across the heavens. What is this thing? Where did it come from? What does it mean? Ancient cultures universally saw comets as omens, usually bad omens. Comets were associated with disasters, wars, plagues, famines, the deaths of kings. They were seen as signs from the gods, warnings of impending doom. The Chinese kept meticulous records of comets. They described their appearances, their paths across the sky, and what disasters followed. They believed that different types of comets predicted different types of calamities. A red comet might mean war. A white comet might mean drought. The Babylonians also recorded comets and treated them as ominous signs. A comet appearing in a certain part of the sky might mean the king was in danger or that a neighboring kingdom would fall. The Greeks and Romans were a bit more skeptical, at least some of them. Aristotle thought comets were atmospheric phenomena, not celestial objects. He believed they were some kind of fiery exhalation in the upper atmosphere. This was wrong, but at least he was trying to explain them naturally rather than supernaturally. The Romans, though, were still pretty superstitious about comets. A comet appeared shortly before Julius Caesar was assassinated, and later it was said to be his soul ascending to heaven. Augustus used this comet in his propaganda, putting it on coins and claiming it showed Caesar's deification. In the Middle Ages, comets continued to be seen as bad omens. The appearance of Halley's Comet in 1066, just before the Norman conquest of England, was interpreted as a sign of the coming upheaval. It's even depicted in the Bayeux Tapestry, with people pointing at it in fear. It wasn't until the 16th and 17th centuries that astronomers started to understand what comets actually were. Tycho Brahe observed a comet in 1577 and determined that it was farther away than the moon, which meant it was a celestial object, not an atmospheric one. Halley figured out that some comets were periodic, returning at predictable intervals. The comet he predicted would return in 1758, now called Halley's Comet, did exactly that, proving that comets were part of the solar system. But to ancient astronomers, comets were mysterious, unpredictable, and frightening. They didn't fit into the orderly cosmos. They appeared without warning and disrupted the heavens. Meteors, shooting stars, were less scary but equally mysterious. Ancient people noticed them, but they usually didn't record them the way they did comets. Meteors were fleeting. They appeared for a second and were gone.
Most ancient cultures thought meteors were atmospheric phenomena, like lightning. The Greeks called them falling stars, but they didn't think actual stars were falling. They thought it was some kind of atmospheric fire. Occasionally, meteorites, rocks from space that actually hit the ground, were found and venerated. The Kaaba in Mecca contains a black stone that may be a meteorite. Several ancient temples had sacred stones that were probably meteorites. But by and large, meteors were curiosities, not objects of serious astronomical study. They were too brief and unpredictable to track systematically. Auroras, the northern and southern lights, were also mysterious to ancient people. They're caused by charged particles from the sun interacting with the Earth's magnetic field, but ancient people didn't know that. They saw shimmering curtains of light in the sky and invented stories to explain them.
In Norse mythology, auroras were the reflections of the Valkyries' armor as they rode across the sky. In Chinese folklore, they were dragons fighting. In some Native American traditions, they were the spirits of ancestors dancing. Auroras are more common at high latitudes, so ancient Mediterranean and Middle Eastern astronomers rarely saw them. When they did, they were often recorded as unusual phenomena, sometimes interpreted as omens. So comets, meteors, and auroras were all part of the ancient sky, but they were outliers. They didn't fit into the regular patterns. They were the exceptions that proved the rule. The heavens were usually orderly and predictable, but occasionally weird stuff happened. Let's drift now to a specific astronomical event that ancient people definitely noticed and sometimes freaked out about: solar eclipses. Solar eclipses, when the sun dies, but only for a few minutes. Solar eclipses are one of the most dramatic astronomical events visible from Earth. The sun, the source of all light and life, suddenly goes dark in the middle of the day. The temperature drops, animals freak out, stars become visible, and then, a few minutes later, the sun comes back. If you didn't know what was happening, this would be absolutely terrifying. Ancient cultures around the world recorded solar eclipses, and they almost always interpreted them as bad omens. The sun was a god in many mythologies, and an eclipse meant the sun god was angry or sick or being attacked. In ancient China, people believed that a dragon was eating the sun during an eclipse. They would bang drums and shoot arrows into the sky to scare the dragon away. And it worked. The dragon always left, and the sun came back. Success. There's a famous story, probably apocryphal, about two Chinese court astronomers, He and Ho, who got drunk and failed to predict an eclipse. The emperor was so angry that he had them executed. Whether or not this actually happened, it shows how seriously eclipses were taken. The Babylonians, as we mentioned earlier, figured out how to predict eclipses using the Saros cycle. This was a huge achievement. If you could predict an eclipse, it wasn't an omen anymore. It was just astronomy. You could tell the king, "Don't worry, we knew this was going to happen," and everyone could relax. But even with prediction, eclipses were still treated with respect and ritual. The Babylonians would perform ceremonies to ward off any evil associated with the eclipse. The ancient Greeks also understood eclipses, at least the educated ones did. Thales supposedly predicted an eclipse, as we mentioned. Anaxagoras, around 450 BCE, explained that eclipses were caused by the moon passing in front of the sun. This was a rational, naturalistic explanation, and it was correct. But even in Greece, where philosophers were trying to understand the cosmos rationally, eclipses were still seen as significant events. Herodotus records an eclipse that stopped a battle between the Lydians and the Medes. Both sides were so freaked out by the sun going dark that they immediately made peace. In the Americas, the Maya could predict eclipses using their tables in the Dresden Codex, but they still saw them as dangerous. Eclipses were times when the boundaries between the physical and spiritual worlds were thin, when malevolent forces could break through. Across the Pacific, Polynesian cultures had various myths about eclipses. In some traditions, the sun and moon were lovers, and an eclipse happened when they embraced. In others, a monster was trying to swallow the sun or moon. Interestingly, total solar eclipses are relatively rare at any given location.
You might go your whole life without seeing one, even though they happen somewhere on Earth every 18 months or so. So for most ancient people, solar eclipses were once-in-a-lifetime events, or maybe never. Lunar eclipses, on the other hand, are more common and visible from anywhere on Earth where the moon is above the horizon. Lunar eclipses happen when the Earth passes between the sun and the moon, casting a shadow on the moon. The moon turns a deep red color, which is pretty eerie. Lunar eclipses were also seen as omens, though generally less frightening than solar eclipses. The moon represented different things in different cultures, often femininity, the night, mystery. An eclipsed moon could mean anything from a threat to the king to problems with childbirth. But lunar eclipses also provided ancient astronomers with useful information. As we mentioned earlier, Aristotle used the round shadow of the Earth on the moon as evidence that the Earth was spherical. Observing multiple lunar eclipses from different locations helped astronomers understand the size and shape of the Earth and the distances to celestial objects. So eclipses were both terrifying portents and valuable scientific data. Ancient astronomers walked this line between superstition and observation, between fear and understanding. Let's move on now to a topic that ancient astronomers thought about a lot but struggled to measure: the distances to celestial objects.
Measuring the unmeasurable, or how far away is the moon anyway? So here's a question that seems simple. How far away is the moon? You can see it, it's right there. But how far is there? 1,000 miles? 1,000,000? 1,000,000,000? Ancient astronomers desperately wanted to know, because if you could measure the distance to the moon, you could start to understand the scale of the cosmos. You could figure out how big the sun was, how far away the planets were, maybe even how far to the stars. But measuring cosmic distances with ancient technology was absurdly difficult. The first person we know of who tried to do this systematically was Aristarchus of Samos, the same guy who proposed a heliocentric model. Around 270 BCE, Aristarchus wrote a treatise called On the Sizes and Distances of the Sun and Moon. His method was clever. During a half moon, the sun, moon, and Earth form a right triangle. The moon is at the right angle. If you can measure the angle between the sun and moon as seen from Earth, you can use trigonometry to figure out the ratio of the distances. Aristarchus measured this angle and got about 87 degrees. From this, he calculated that the sun was about 19 times farther away than the moon. This was wrong. The actual angle is about 89.85 degrees, and the sun is actually about 400 times farther away. But the method was sound. The problem was that the angle was really hard to measure accurately. Still, Aristarchus had shown that the sun was much farther away than the moon, and therefore much bigger. Because the sun and moon appear to be about the same size in the sky, but if the sun is farther away, it must be physically larger. Aristarchus calculated that the sun was about 6 to 7 times larger in diameter than the Earth. Again, this was an underestimate. The sun is actually about 109 times larger, but it was in the right ballpark. Later, Hipparchus, around 150 BCE, used a different method to measure the distance to the moon. He observed a solar eclipse from 2 different locations and used parallax, the apparent shift in the moon's position against the background sky, to calculate its distance. Hipparchus got a pretty good estimate, about 60 Earth radii, or roughly 380,000 kilometers. The actual average distance is about 384,400 kilometers, so he was impressively close. From the moon's distance, Hipparchus could also estimate its size. If you know how far away something is and how big it appears, you can calculate its actual size. Hipparchus figured out that the moon was about 1/4 the diameter of the Earth, which is correct. Ptolemy, in the 2nd century CE, refined these measurements and included them in the Almagest. He also tried to estimate the distance to the sun, though his methods were less accurate. Ptolemy's cosmos was still geocentric, with everything orbiting the Earth, so he placed the sun farther away than the moon, but closer than the stars. The problem with measuring distances to the stars was that they showed no parallax.
No matter where you observed from, no matter what time of year, the stars appeared to be in the same positions relative to each other. This meant either they were incredibly far away, so far that parallax was too small to measure, or the Earth wasn't moving. Most ancient astronomers chose the second option. It seemed obvious that the Earth was stationary, so the lack of stellar parallax wasn't a problem. The stars were just attached to a distant celestial sphere that rotated around the Earth. But a few thinkers, like Aristarchus, argued that if the Earth was moving, the stars had to be unimaginably distant. This was hard for people to accept. It made humans seem insignificant, lost in a vast cosmos. It was philosophically and emotionally difficult. So for most of ancient history, the scale of the universe was underestimated. People thought the moon was relatively close, which it is by cosmic standards. They thought the sun was maybe a few million kilometers away, which is way too close. And they thought the stars were maybe just beyond the sun, on a distant sphere, which is hilariously wrong. It wasn't until the 16th and 17th centuries, with the work of Copernicus, Galileo, and Kepler, that people started to grasp the true scale of the solar system. And it wasn't until 1838 that Frederick Bessel measured the parallax of a star and proved that stars were light years away. But ancient astronomers tried. They used geometry, they used observations, they used logic. They didn't have the tools to get it right, but they laid the groundwork. Now let's talk about something ancient astronomers were better at, tracking the wandering stars, also known as planets. The Wanderers, tracking Mercury, Venus, Mars, Jupiter, and Saturn. The ancient Greeks called them Planetary, which means wanderers. The 5 visible planets, Mercury, Venus, Mars, Jupiter, and Saturn, don't stay in one place like the stars. They move across the zodiac, sometimes quickly, sometimes slowly, sometimes even backward. This retrograde motion was deeply puzzling to ancient astronomers. Why would a planet suddenly reverse direction, move backward for a while, then reverse again and continue forward? We know now that retrograde motion is an optical illusion caused by the relative speeds of Earth and the other planets in their orbits. When Earth overtakes Mars, for example, Mars appears to move backward against the background stars, even though it's actually continuing forward in its orbit. But ancient astronomers didn't know about orbits. They thought planets moved in complex paths around the Earth. Explaining retrograde motion required elaborate geometric models. Let's talk about each planet individually, because ancient astronomers noticed they all behaved differently. Mercury is the closest planet to the Sun, though ancient people didn't know that. What they knew was that Mercury was hard to see. It's always close to the Sun in the sky, appearing either just before sunrise or just after sunset. It never gets far from the Sun and moves quickly. The name Mercury comes from the Roman messenger god who was known for his speed. The Babylonians tracked Mercury carefully, noting its appearances and disappearances. They figured out its synodic period, the time it takes to return to the same position relative to the Sun, which is about 116 days. The Greeks struggled with Mercury. Its motion was erratic and hard to predict. Ptolemy's model for Mercury was particularly convoluted, requiring multiple epicycles to match observations.
Venus is the brightest object in the night sky after the moon. It appears as the morning star before dawn or the evening star after sunset, and it's absolutely brilliant. Ancient cultures all noticed Venus and gave it special significance. The Babylonians realized that the morning star and evening star were the same object. They tracked Venus meticulously, and as we mentioned earlier, the Maya were obsessed with it. Venus has a synodic period of about 584 days. It appears in the evening sky for about 263 days, disappears for about 50 days, appears in the morning sky for another 263 days, then disappears for about 8 days before starting the cycle again. The Greeks and Romans associated Venus with love and beauty, Aphrodite, Venus, because it was so beautiful and bright. But the Babylonians and Maya associated it with war and violence. Different cultures, different interpretations. Mars is the red planet, and its color made ancient people associated with blood and war. The Romans named it Mars after their war god.
Mars is interesting because its brightness varies dramatically. When it's at opposition, on the opposite side of the sky from the Sun, which means it's relatively close to Earth, it's very bright, nearly as bright as Jupiter, but at other times it's much dimmer. Mars also has prominent retrograde motion. Its retrograde loops are large and obvious, which made it a challenge for geocentric models. The Babylonians tracked Mars carefully and developed tables for predicting its position. The Greeks incorporated it into their geometric models, adding epicycles to account for its retrograde motion. Jupiter is the largest planet, and it's correspondingly bright and majestic. The Romans named it after their king of the gods. Jupiter moves slowly through the zodiac, taking about 12 years to complete a full circuit. The ancient Chinese divided the zodiac into 12 sections, one for each year of Jupiter's cycle. This became the basis for the Chinese zodiac system, though later the zodiac was associated with different animals. Jupiter's retrograde motion is less pronounced than Mars, but it's still noticeable. Ancient astronomers tracked it carefully, and it played an important role in astrological predictions. Saturn is the slowest of the visible planets, taking about 29.5 years to orbit the zodiac. It's dimmer than Jupiter or Mars, but still clearly visible. The Romans named Saturn after the god of time and agriculture, probably because of its slow, steady movement. In astrology, Saturn was often associated with misfortune, delays, and hard lessons. Saturn's retrograde motion is subtle, but ancient astronomers noticed it. Tracking Saturn required patience because you had to observe it for years to see its complete motion. All 5 of these planets were incorporated into astrological systems. Their positions at the time of someone's birth were thought to influence their personality and fate. Their movements were interpreted as omens affecting kingdoms and rulers. But beyond astrology, tracking the planets was a serious scientific endeavor. Ancient astronomers spent lifetimes recording planetary positions, looking for patterns, developing mathematical models. The Babylonians compiled tables that could predict planetary positions years in advance. The Greeks built geometric models that could account for retrograde motion. Indian astronomers calculated planetary periods with remarkable accuracy. None of them understood that planets orbit the sun, none of them knew about gravity, but they understood that planetary motion followed rules, and they did their best to figure out what those rules were. And in doing so, they laid the foundation for modern astronomy. When Copernicus, Kepler, and Newton finally figured out how the solar system actually worked, they were building on thousands of years of careful observation by ancient astronomers who tracked the wandering stars night after night, year after year, century after century. Let's drift now to something a bit more abstract. How ancient astronomers thought about the cosmos as a whole. What did they think the universe looked like? Cosmology. What ancient people thought the universe looked like. Spoiler, they were creative. Ancient cosmologies are fascinating because they're a mix of observation, philosophy, and mythology. People were trying to make sense of the universe with limited information, and they came up with some truly wild ideas. Let's start with the Babylonians. They thought the Earth was a flat disk floating on a cosmic ocean. Above the Earth was the sky, which was a solid dome, the firmament. The stars were holes in this dome, or maybe lights attached to it. The sun, moon, and planets moved across the sky, but they weren't infinitely far away. They were relatively close, just above the dome. Below the Earth was the underworld, the realm of the dead. The whole structure was surrounded by water, cosmic water, primordial water. This water was held back by the dome of the sky and the floor of the Earth, but occasionally it leaked through, causing rain from above or springs from below.
This cosmology made sense given what they could observe. The sky does look like a dome. The Earth does seem flat if you can't see very far, and water is everywhere. Rivers, seas, rain. So it makes sense that water would be a fundamental cosmic element. The ancient Egyptians had a similar idea, but with more gods. The sky was the goddess Nut, arching over the earth. The earth was the god Geb, lying beneath her. The air between them was the god Shu, holding them apart. The sun god Ra traveled across Nut's body during the day in a boat. then journeyed through the underworld at night to rise again in the east. The Egyptians also thought the Nile had a cosmic counterpart, a celestial Nile that flowed through the heavens. The stars were seen as boats or as manifestations of gods and the blessed dead. In ancient India, cosmology was incredibly elaborate and operated on vast timescales. The universe went through endless cycles of creation and destruction, each lasting billions of years. The Earth was one of many worlds, stacked in layers. Mount Meru stood at the center of the world, and around it were continents, oceans, and various realms of gods and demons. The cosmos was held up by elephants standing on a turtle which floated in a cosmic ocean. This is the classic image, though different texts describe it differently. The important thing is that Indian cosmology was less about physical structure and more about spiritual and philosophical concepts. Chinese cosmology also had the Earth at the center, with the heavens above. But Chinese thinkers debated whether the sky was a solid dome or an infinite void. Some schools of thought argued for a dome, the heavens as a ceiling above the Earth. Others argued that the sky was empty space extending infinitely, with the sun, moon, and stars moving freely through it. The Chinese also believed in a fundamental duality, yin and yang. The Earth was yin, dark and passive. The heavens were yang, bright and active. These forces were constantly interacting, creating the changes observed in nature. Now let's get to the Greeks, because Greek cosmology was where things got really interesting and really complicated. Early Greek thinkers like Thales and Anaximander proposed various cosmic structures. Thales thought the Earth floated on water. Anaximander thought the Earth was a cylinder suspended in space, with the stars, sun, and moon revolving around it on wheels of fire. But the Greeks who really shaped Western cosmology were the Pythagoreans and their intellectual descendants. The Pythagoreans, as we mentioned, believed the universe was fundamentally mathematical. They also believed in a central fire around which everything revolved: the Earth, moon, sun, planets, and stars. This wasn't quite heliocentrism because the central fire wasn't the sun, but it was an interesting attempt to explain why celestial objects moved. Plato, in the 4th century BCE, proposed that the universe was made of perfect geometric forms. The stars were on a perfect sphere, the outermost sphere of the cosmos. Inside that were the spheres of the planets, sun, and moon, each rotating at different speeds. The Earth sat at the center, stationary and spherical. Plato's student, Aristotle, refined this into a comprehensive cosmological system. Aristotle's cosmos had the Earth at the center, surrounded by concentric crystalline spheres. Each celestial object was embedded in a sphere, and the spheres rotated to carry the objects around the sky. The region below the moon, the sublunar realm, was imperfect and changeable. Things were born, grew, and died. The 4 elements, earth, water, air, fire, mixed and separated. But the region above the moon was perfect and unchanging. The celestial spheres were made of a 5th element, the aether, which was eternal and incorruptible. The celestial bodies moved in perfect circles because circles were the most perfect shape. This model dominated Western thought for nearly 2,000 years. It was adopted by Islamic astronomers, incorporated into Christian theology, and taught in universities until the scientific revolution. Ptolemy's Almagest provided the mathematical details for this cosmology. His geocentric model, with its epicycles and deferents, could predict planetary positions with reasonable accuracy. It wasn't simple, but it worked. In the Americas, cosmologies were different again. The Maya believed in multiple layers of the cosmos: the heavens above, the earth in the middle, and the underworld below. Each layer had 9 levels, and gods and spirits moved between them. The Inca had a similar layered cosmology. The sky, Hanan Pacha, was the upper world, home of the gods and celestial objects. Kai Pacha was the world of the living. Uku Pacha was the underworld, the world of the dead and of germination. Across the Pacific,
Polynesian cosmologies varied by island and culture, but many involved a series of heavens stacked above the earth, with the gods residing in the highest heavens. What's striking about all these cosmologies is that they tried to create a unified picture of the cosmos. They tried to explain not just where things were, but why they were that way. They incorporated observations, myths, philosophy, and theology into comprehensive worldviews. And while they were all wrong in their specifics, the Earth isn't flat, the sky isn't a dome, the sun doesn't orbit the Earth, they represented humanity's best efforts to understand the universe with the information available. It wasn't until the telescope that people could really start to see how wrong these models were. And it wasn't until Newton that people had a theoretical framework to replace Aristotle's spheres. But ancient cosmologies weren't just wrong guesses. They were the foundation on which modern science was built. They represented thousands of years of observation, thought, and debate. They were humanity looking up at the sky and asking, what is all this? And that question, that drive to understand, is what makes us human. Let's close out by talking about what all this ancient astronomy actually meant. What was the point?
Why it mattered. Or, what's the point of staring at dots in the sky for your entire life? So we've spent a couple hours now talking about ancient people staring at the sky, recording the positions of stars, tracking the phases of the moon, calculating eclipse cycles, building giant stone monuments aligned with the solstices. And you might be wondering, why? What was the point? Well, as we've touched on throughout, ancient astronomy served multiple purposes. It was practical, it was religious, it was political, and eventually it was scientific. Let's start with the practical. If you're an ancient farmer, knowing when to plant and harvest is a matter of survival. Plant too early, and a late frost kills your crops. Plant too late, and you don't have time to harvest before winter. The sky, specifically the position of the sun and the appearance of certain stars, gave you a reliable calendar. The Egyptians used the heliacal rising of Sirius to predict the Nile flood. The ancient Greeks used the rising and setting of various stars to mark agricultural seasons. Hesiod, a Greek poet from around 700 BCE, wrote a farming manual called Works and Days that's full of astronomical references. When the Pleiades rise, begin your harvest. When they set, begin plowing. So astronomy was directly tied to food production, which was the foundation of civilization. Astronomy was also essential for navigation. Polynesian wayfinders used star paths to cross thousands of miles of ocean. Arab and European sailors used the position of the North Star to determine latitude. Knowing the stars meant knowing where you were and where you were going. Then there was the religious aspect. In almost every ancient culture, the sky was sacred. The sun was a god. The moon was a goddess. The planets were divine beings. Eclipses were cosmic battles or omens from heaven. Religious rituals were timed according to the calendar, and the calendar was based on astronomical observations. The full moon, the new moon, the solstices, the equinoxes. These were all religiously significant. Temples and monuments were built with astronomical alignments, not just for practical reasons, but to connect the earthly and the divine. When sunlight streamed through a temple window at the exact moment of the solstice, it was a manifestation of the god's presence. Astronomy was also political. Rulers who could predict celestial events, especially scary ones like eclipses, had power. They could claim divine favor or special knowledge. They could use astronomical omens to justify wars, political decisions, or social policies. In China, the emperor's legitimacy depended on the mandate of heaven, and celestial events were interpreted as signs of whether the heavens approved of the emperor's rule. If an eclipse happened and the emperor hadn't been warned, it could be used by rivals to challenge his authority.
In Babylon, if a lunar eclipse was predicted to harm the king, they'd put a substitute king on the throne for the duration of the eclipse, then quietly kill the substitute afterward. The real king would be safe, and the omen would have been fulfilled. Sneaky, but effective. So astronomy was a tool of statecraft, a way to maintain power and control. And then, eventually, astronomy became something else, a pursuit of knowledge for its own sake. Greek philosophers looked at the sky and asked questions, not because they needed to for farming or religion or politics, but because they wanted to understand. Why do the planets move the way they do? How far away are the stars? What are they made of? Is the cosmos finite or infinite? These were philosophical questions, driven by curiosity. This is where science begins, not with the complete abandonment of religion or practicality, but with the addition of a new motivation, understanding the universe as an end in itself. Ancient astronomers didn't have telescopes, spectrometers, or space probes. They couldn't see the moons of Jupiter or the rings of Saturn. They couldn't analyze the composition of stars or detect distant galaxies. But they could observe. They could record. They could think. They could calculate. And they could pass their knowledge on to the next generation, who would add to it and pass it on again. Over thousands of years, this accumulated knowledge became a framework for understanding the cosmos. It was incomplete and often wrong, but it was real progress. When Copernicus proposed his heliocentric model in the 16th century, he was building on Greek and Islamic astronomy. When Galileo pointed his telescope at the sky in 1609, he was testing ideas that had been debated for centuries. When Newton formulated his laws of motion and gravity in the 17th century, he was explaining phenomena that ancient astronomers had observed and tried to understand. Modern astronomy stands on the shoulders of giants, and some of those giants lived thousands of years ago, sitting on top of ziggurats, watching the moon move through the zodiac and writing it down on clay tablets. So what was the point of ancient astronomy? The point was survival. The point was religion. The point was power. And eventually, the point was knowledge. Ancient people looked up at the night sky and saw order in the chaos. They saw patterns in the movements of celestial objects. They realized that the universe was comprehensible, that it followed rules, that it could be understood. And that realization, that the cosmos is knowable, is maybe the most important idea in the history of human thought. It's the foundation of science. It's why we have telescopes and spacecraft and theories about the Big Bang and the expansion of the universe. It all started with someone, somewhere, thousands of years ago, looking up at the night sky and deciding to pay attention, to watch, to record, to try to understand. And yeah, maybe they were motivated by the need to know when to plant wheat, or by the desire to predict omens, or by the fear of angering the gods. But somewhere along the way, they also became curious. They started asking questions, and they passed those questions on to us. So, the next time you look up at the night sky, and you should, by the way, because it's beautiful and it's yours, remember that you're looking at the same stars ancient people saw. The constellations have shifted slightly due to precession, and there's a lot more light pollution now, but the sky is fundamentally the same. The difference is we know more. We know the stars are distant suns. We know the planets orbit the sun, not the Earth. We know the universe is billions of years old and unimaginably vast. But we only know these things because thousands of people over thousands of years watched the sky, wondered, and wrote it down. And that's kind of beautiful. All right, we've been talking for a while now. I hope you're feeling relaxed, maybe a little sleepy. That's the goal, after all. Ancient astronomy is endlessly fascinating, but it's also perfect for drifting off to. So if you're still awake,
Thanks for sticking with me through this long journey across time and space. And if you've already fallen asleep, well, sweet dreams. May you dream of perfect circles, epicycles, and the heliacal rising of Sirius. Until next time, keep looking up. And maybe grab a notebook. You never know. You might be the next Hipparchus. Good night.